Find the following limit. Here is a rational function. We're taking the limit as x approaches infinity, and we want to know what this equals to. Well, remember that this is the definition of how to find a horizontal asymptotes. Okay? And if we have a rational function, then the horizontal asymptotes can be found using one of these three cases. Okay? Go ahead and go to example 1. So we look at the degree. We compare the degree of the numerator, of the leading term for the numerator and the leading term for the denominator. Since they are the same, it falls into case 2. So what does case 2 tell us? It tells us that the horizontal asymptotes is just a over b. In other words, it is equal to 3 over 4 because a is 3 and b is 4. Okay, good. Go on to example number 2, and we're going to compare the power. So if you look carefully at the power, another rational function, limit as x approaches negative infinity. So we're going to go ahead and compare the power. Well, because the power, the top power is smaller than the bottom power, so 1 is less than 2. So 1 is less than 2. So it falls into case 1. What does case 1 tell us? The horizontal asymptotes is y equals to 0. Our interpretation, well, the answer is just 0. Okay, so if it falls in case 1, it's always going to equal to 0. Go on to example number 3. Now, in order to compare the power, why don't we rearrange this so that it's in decreasing degree of x? I would rewrite the problem as leave the numerator alone. In the denominator, go ahead and flip these, so negative x plus 2. Okay, so now we go ahead and we compare the degree of the numerator and the denominator. And if you look carefully at the degree, they are the same. And if they are the same, then it falls in case 2. Remember that? And if it falls in case 2, then it equals to a over b. A is 1 and b is negative 1. So 1 over negative 1 is negative 1. That's the limit of that problem. Okay? Great job. Let's go on to example number 4. Take the leading degree and compare it. This is how we find the limit as x approaches infinity. Okay, x is going to grow really big. So top is bigger than bottom. Top bigger than bottom. None. Okay, so does not exist. None. Okay, awesome, good. We're going to go ahead and talk about some of the growth rate. Which function grows faster than other? So I rearranged 4 functions here from the slowest to the fastest. The name of this function is called logarithmic. So this is log. Okay. This is polynomial. For example, x squared, x cubed, these are polynomial. Okay. This is exponential function, exponential. E to the x, 2 to the x, 3 to the x, these are types of exponential functions. And the last one is factorial function. So something like that, that's a factorial function. We want to know which function grows the fastest. Well, log grows the slowest. It's actually very slow, followed by polynomial. It's actually faster than log. And by the way, a linear function is also a polynomial. So these are polynomial. Exponential is faster than polynomial, and factorial is the fastest. So I line them up there for you from slowest to fastest. Okay? This is going to help us find the limit as x approaches infinity. In the previous page, I show you how to find the limit as x approaches infinity when we have rational functions. In other words, top is a polynomial, bottom is a polynomial. In our case now, top is not a polynomial. The bottom is a polynomial. So we're going to have a mixture between polynomial and non-polynomials. Okay? So the way how we find the limit for these is we analyze their growth rate. Remember, this log grows the slowest, and then factorial is the fastest. Okay? So I look at this function, and because I want to know how it behaves at infinity, I need to study its growth rate. So I know that I'm comparing, this is an exponential function, guys. See? So I know that the top is exponential. The bottom is polynomial. And as you can see, exponential is faster than polynomial. Okay? Because that's ahead of polynomial. Exponential is faster than polynomial. So why don't I go like this? I'm going to go, this is a fast growing function comparing to a polynomial, which is really slow comparing to exponential. So if the numerator grows faster than the denominator, then your answer is infinity. Okay, so if numerator is faster than denominator, answer is infinity. Awesome. Look at problem number 5. The numerator is exponential. The denominator is also exponential. So what? They grow at the same rate. So they both grow at the same rate. What does that mean? If they grow at the same rate, guys, then we take their coefficients as the value for our limit, or as our answer. So because they're both exponential, they grow at the same rate, therefore 3/2 is gonna be our answer. And we're done with that part. Okay, good. So make sure you review the growth rate, so on and so forth. Now, I didn't do a problem where the bottom is faster than the top, but let's say if we add in example 6 over here, and if we flip this problem around, like let's say if I were to give you the limit as x approaches infinity of, let's say, x squared, and then you have log of 10 of x. Okay, well, how do we evaluate this limit? When we look at their growth rate, because these are not both rational functions, they're not both polynomials, so we can't use the rational function property. Well, we have to kind of use the growth rate their growth rate to determine the value. Log is the slowest, so why don't you put slow on top? Exponential is faster than log because we're just comparing the two functions. Put fast at the bottom. Okay. If the function at the bottom grows faster than the function at the top, then your limit is always going to equal to 0. Think about it. If this is a small number and this is a really big number, then a small number over a really big number is 0. So if denominator is fast and numerator is slow, answer is 0 because this function, the denominator is going to be really big. The numerator is going to be really small. So small over big is 0. Awesome. Go flip to the back of this page. Alright, so this is just a review of reading graph to analyze functions. Okay, make sure you know how to do this well. I want to know what is the value as x approaches 0 from the right. So from the left. So from the left, as x approaches 0 from the left, here's 0. I have to analyze this function. The function wants to take on the value of -2. Okay, x approaches 0 from the right. Okay, from the right, I have to track down this function, and it wants to take on the value of 2. So what is the limit? Well, the limit of the function is 0 because the left end and the right end doesn't equal to each other. Or you can also say that there's a jump at 0. Okay, good. What is the limit as x approaches 1 from the left? So x approaches 1 from the left. Coming from the left, I have to use this graph, and that equals to 3. It wants to take on the value of 3. As I approach 1 from the right, okay, I have to use this graph, and it seems that it also wants to take on the value of 3. Okay, 1 from the right takes on the value of 3. So what's the limit of the function as x approaches 1? Well, it's 3 because the limit from the left equals to the limit from the right. That's the definition of a limit, so it equals to 3. Great job. What's the limit as x approaches 0? As x approaches 0, the limit is 4. Okay, good. Go on to problem number 8. Okay, what is the limit as x approaches 1? Well, as x approaches 1 this way, from the left, you get -infinity. What's the limit as x approaches +1? Well, as x approaches +1, sorry about the zooming issue there. As x approaches +1 from the right, you get infinity. The limit does not exist because they take on different values. Okay, what is the limit as x approaches infinity? Okay, so as x gets really big, if you look carefully, the function wants to approach 0. Okay, so the function wants to approach 0 as x gets really big. What happens when x gets really big? -infinity. Well, as x gets really big in the negative direction, the function also wants to approach 0. So we put 0 there. Awesome. I'll see you guys in class.